In this video and the next, let's go through two examples that involve the application of the central limit theorem, and then consider the rare event rule when we draw our conclusions. So let's review the rare event rule. If, under a given assumption, the probability of a particular observed event is extremely small, such as less than 0.05, that's what we typically use as our cutoff point, we conclude that the assumption is probably not correct. We test a claim by distinguishing between two different things. The first is that an event that easily occurs by chance. So we want to distinguish between that and an event that is highly unlikely to occur by chance. Okay, and that's that 0.05 cutoff. An event that easily occurs by chance, it has a greater than 5% chance of occurring, and an event that's highly unlikely to occur by chance, and that's that below 0.05 or 0.05 and below. So let's look at an example. The Atlas Barbell Company makes bars for weightlifting. The weights of the bars are normally distributed with a mean of 720 ounces, that's 45 pounds, and a standard deviation of 4 ounces. So suppose we randomly select 10 bars and find that their mean weight is 723 ounces. Find the probability that a sample of 10 bars will have a mean weight of 723 ounces or greater. So let's note some of the things that we see here, the information we're given. We're given that the population mean is 720 ounces. This is our assumption. The people that make these bars, this is what they had intended, what they're assuming, what they had set up their manufacturing process to do, make bars that had a mean of 720 ounces. So that's their assumption that that's what they're doing. The standard deviation is 4 ounces. And we're going to select a sample size of 10 bars. So we've pulled out of this the data that we need. Now the first question is, does the central limit theorem apply? Well, this sample size is awfully small. That's less than the 30 that we have used as our cutoff point for central limit theorem, but remember it says the weights of the bars are normally distributed. So the original data is normally distributed. That means the sample size doesn't matter. We can have small sample sizes. So yes, since the original population is normally distributed, we can use the central limit theorem. Okay, so let's sketch, label, and shade our curve. Okay, on our X scale, and it's the mean weight, it's the mean for a sample, so X bar, we had 720 is our mean. And of course, on the Z scale, let's see, I'll do that here. If we change this to the standard normal, then the mean is always 0. So I want to get both of my scales set up. Now what we're interested in is that the weight of the mean weight of the sample is greater than or equal to 723 ounces. So I want this area. Okay, so let's note a couple of things. We have the mean for our samples, the mean of the sample means, is the same thing as the population mean. We've seen that before, and that's 720. Okay, the standard deviation of our sample means, well, that's equal to the standard deviation of the population divided by the square root of the sample size. Okay, so we have 4 over the square root of n. I'm sorry, square root of 10. Let's see if I can fix that. Square root of 10. Okay, so I could reduce this to a decimal, then I'd do some rounding, and I'd add some rounding error. I prefer to leave it just like this and then use it in my calculation that way. Alright, so what we need to find out is what is the z-score right here for 723. Alright, so let me come over here. Z is equal to x bar minus the mean of the sample means over the standard deviation of the sample means. Okay, well our x bar, our mean for this sample, our sample mean is 723. We said our mean of our sample means is the same as the population, 720. And sigma, our standard deviation for the sample means, is 4 over the square root of 10. But now, please be careful here. If you don't, as you put this in your calculator, if you don't put this in parentheses, you may very well get the wrong answer. Your calculator will take this difference, divide by 4, and then divide that by the square root of 10, which is not what you're trying to do. So be careful. Alright, so when I run through this calculation, I got 2.3717 and on, but this is a z-score, so I know I want 2 decimal places, 2.37. So now I know what goes here, 2.37. The associated z-score for 723 is 2.37. So now I can find my probability. Okay, so the probability, this is the question, what's the probability that the sample mean would be greater than or equal to, remember it doesn't matter because the probability that any one value exactly, that x bar is any one value, is 0. So it doesn't matter if I use greater than or equal to. Well, that's the same thing as the probability that z is greater than or equal to 2.37, my associated z-score. And what I will use for that, I'm going to go ahead and write it here, so you'll have that notation. The normal CDF function on the TI-8384, and I'll put in my low value, 2.37, and we are using for positive infinity, 5. 2.37 and 5. Let's see. Okay. So we want our distributions, the second one, normal CDF, 2.37, comma, 5. And we get 0.00889. We're going to round to 4, so I'll write those 5 down. 0.00889. Write it here. 0.00889, so rounded to 4, 0.0089. Okay, so now we have to interpret our results. Okay, the probability of getting a sample mean, the probability of getting a sample mean at least as high as 723 ounces Remember, that's what we were asked to find. Find the probability of getting a sample mean at least as high as 723 ounces. So I'm answering that question in a nice sentence here that summarizes it. Assuming the population mean, remember our assumption, assuming the population mean is 720 ounces, is, this is what we found, 0.0089. Okay, so notice that's a very small probability. But because we actually did obtain a sample of 10 bars with a mean of 723 ounces, there are two possible explanations for what just happened. So let's look at those. Alright, so two possible explanations. The first one is that the population mean is actually, that the population mean really is 720 ounces. So the population mean really is 720 ounces, and the sample represents an event that is extremely rare. I mean, look what we found, 0.0089, well below our 0.05 of what we consider usual and unusual. So here's one explanation, that the population mean really is 720 ounces, and we just saw some extremely rare occurrence. Okay? A second possible explanation is the population mean is actually greater than 720 ounces. And the sample mean is typical. Well, since the probability of 0.0089 is so low, it seems more reasonable to assume or conclude that the population mean is greater than 720 ounces, number 2 here. It appears that the bars are being manufactured at a weight greater than 720 ounces. It appears that our assumption was wrong and that the population mean is actually greater than 720 ounces. So while this difference in weight maybe isn't all that much, the manufacturer may want to make some adjustments. I mean, they're making the bars, they're using more materials than they had intended, and they're making the bars heavier than maybe what their customers are requesting. And so it really just depends on the established tolerances and customer demands as to whether or not they're going to make a change. But this tells the manufacturer that their assumption that they're making bars at a mean weight of 720 ounces is wrong. Okay, so that's how we can use the rare event rule when working problems like these and in doing this kind of sampling.